Hello. Today I'll describe a new communication technology that is almost perfectly suited for space applications. It's called laser or free space optical, or FSO communications. Space agencies are interested in FSO because it has the capacity to transmit data faster, the hardware is smaller and lighter, it provides more secure communications, and it uses much less power than radio frequency or RF methods. It's more secure and uses less power because the beam is very narrow compared to RF. That narrow beam then leads to a disadvantage. The beam requires very precise pointing and tracking for long-range applications. FSO's fast data transmission is a result of the higher frequencies for optical and infrared wavelengths compared to those for radio and microwave. Laser beams can transmit digital data using several methods. Here are 4 of these. 1. You can turn the beam on and off. 2. You can rotate the optical wave's polarization to one of 2 states. 3. You can shift the phase. And 4. You can use pulse position modulation. Each method offers distinct advantages and disadvantages. All electromagnetic beams spread after passing through an aperture. Assuming that the output aperture or antenna is circular, the half-spread angle is given by the equation I now show. In this equation, lambda is the wavelength of the light, and d is the diameter of the aperture. This half-spread angle defines the target spot radius, or reception area, at the receiver. Now let's compare an RF beam to a laser beam. Assume that both beams have the same output aperture diameter and power, but the laser's wavelength is 1,000 times smaller than the RF beam's wavelength. The power density of the laser beam at the receiver is 1,000,000 times larger than the RF beam's power density. That's because power density on target is proportional to 1 over the square of wavelength. Obviously then, laser communication requires much less transmitted power than RF. On 18 October 2013, NASA's Lunar Laser Communication Demonstration, or LLCD, made history by transmitting data from lunar orbit to Earth at a rate of 622 megabits per second. That download rate is more than 6 times faster than previous RF systems flown to the moon, and it was accomplished using a solid-state pulsed laser with an average output power level equal to less than 1 watt. It would be too difficult to prove it here, but received data rate is proportional to received power level. Therefore, radio frequency communications cannot be used to transmit video from Mars to Earth, but it can be done with FSO. On 22 August 2016, I briefed my design to NASA for doing this. If you want to learn more about FSO communications, I recommend my book, Free Space Laser Communications: An Introduction. Before I go, I need to remind you that FSO is not ideally suited for communications inside Earth's atmosphere because laser beams are affected by clear air turbulence, fog, rain, snow, dust, clouds, and smoke. Thank you for taking the time to watch this video. Don't forget to like the video if you find it informative or useful.